All right. So close your binders up and let's review what you know about absolute dating. All right. Close them up. Raise your hand and tell me, what is absolute dating? What is that? Close your binders up. Binders should be closed. Bryson.
Finding out the exact age of something.
Finding out the exact age of something. So we're finding out the absolute age of something. And we find out using stuff like what?
Time.
Time. And time can be recorded with what?
Numbers?
Numbers, like years, months, days, dates, weeks, seconds. All of that signifies time. Every time a second passes, you are a second older. Every time an hour passes, you're an hour older. A day older. And so on and so forth. But that is absolute dating. We do understand that absolute dating and absolute age are interchangeable terms. If we're dating something using absolute terms, then we're finding the absolute age of that something. Okay? All right. So with that being said, what do we use to find absolute age? What are we using, Simon? Radiometric dating. And what is radiometric dating? What is that? What type of thing? How do we do radiometric dating? We have to find the index fossil. So absolute dating uses something called radiometric dating by using these things called index fossils. Good. Now, what is this sentence saying to us for real? Read it for a moment on your own, and then put your hand up and kind of interpret this for me. Take about 20 seconds to read that sentence, and then interpret it for me. Rogerlyn.
It's basically saying that radiometric dating uses the rate of how something, the rate of how something breaks down. For a radioactive element located in index fossils, and index fossils are fossils found in one particular geometric dating.
Geometric?
Geologic.
Okay. Someone else add something to that, Jayla?
So basically, index fossils help determine the absolute age using the radiometric dating.
Okay, but we gotta get some more information in there. Anyone else? Bryson, want to add something?
They use the decay to use the right layer's age.
Okay, we're on the right track. Basically, what this is saying is, let me ask you this. If in the very beginning of time, first of all, a fossil is an indication of what? Past life. So if it's a fossil, that means that there was past life there, correct?
Yes.
All right, at the very moment that the organism dies and the fossil's there, there's going to be 100% of the element that's in that fossil, also known as an isotope. 100% of it, because every living thing is made up of elements. So whatever element is located there, it's going to be 100% of it. That means, has there been any decay?
No.
No, which means it's stable or unstable?
Stable.
It's stable. But as it decays, radiometric dating is going to use the rate of decay. What does it mean, rate of? The speed, how fast it decays. They're going to use their speed or how fast it decays within that fossil to indicate its absolute age. Now, in using this index fossil, this is how they're going to determine absolute age. But first of all, what is an index fossil again, Rogerlyn?
It's a fossil that's found in one geologic.
Fossil that's found in one geologic age. Yesterday, did we draw a geologic column?
Yes.
Okay, good. So we're good. All right, thank you. Thank you. All right. So we do understand that it's a fossil in one geologic age. So using this decay that I just kind of broke down to you, what is that type of decay that we use to find absolute age? What is that decay called? Started with an R.
Radiometric?
Radioactive decay. So what happens is, over a certain amount of time, an element will decay. It has a steady rate of decay. What does that mean, steady rates? Ray? It's constant, meaning that it's not going to fluctuate, it's not going to change. It's going to decay at the same rate. And it decays by half-life. And what that means is it only takes half of the life of what's there in a certain amount of time, and that time is always going to be the same. So for instance, if the half-life is 5 seconds, it's going to remain 5 seconds. And what that means is half of the stable element that's there is going to go away after its half-life. So after 5 seconds, half of it's going to be gone. After another 5 seconds, another half's going to be gone. And after another 5 seconds, another half is going to be gone. So I'm just going to show you just a little bit of an example up here, just so you understand. And we're going to do some examples as well. So by the end of class, you will totally understand what it is that we're talking about. So, in the very beginning, we'll start off with the whole element. Let's say it has a half-life of 5 seconds. So after 5 seconds, half of the stable element is going to decay. And that's going to become unstable. So after 5 seconds, we're going to be able to get rid of half. Let the shaded part represent the decay. Okay? Then after another 5 seconds, first of all, what do we have left? Half, which is how much? What percent? 50%, or 1/2. After 5 seconds, half of the life that's there, the stable amount, is going to go away. So 5 seconds, we're going to get half of this. How much time has passed thus far?
10 seconds.
10 seconds. You got 5 seconds for this, 5 seconds for this. Excuse me. After another 5 seconds, half of whatever is left is going to decay, which is going to leave us with what?
25%.
What?
Alright, so after 5, what do we have left this far? We have 25%, also known as what fraction? A fourth. So after 5 seconds, we have to get rid of half of what's there. This is what's stable. Shh. This is what's stable. So we have to decay part of the stable for half-life. So we'll take half of this. How much time has passed?
15.
Nope. To get from here to here.
5.
5 seconds. We have 1/4 still stable. After 5 seconds, what's going to happen? We're going to take half of what's there. It's half of the life that's there. It's another 5 seconds. Half of a fourth is? Half of a fourth is an eighth. How do you say half of a fourth is an eighth? Is it? How would you possibly, looking at this, look, 1/4, half of a fourth is an eighth. We got a fourth here. We took half of it. We're left with an eighth. Well, we're not going to cut that in half. If we did, it would be 1/16. But we're not going to cut that in half. We're going to look at this and say, all right, if we were paleontologists, what's a paleontologist? Duran? Nope. That's not what they study. They don't just study fossils. Fossils indicate, leave that alone, Ladrika. Fossils indicate what? Madison. Past life. So paleontologists study past life. So let's say you are a paleontologist and you dig up a rock layer and you locate a fossil and all you find is 1/8. And you know that the half-life is 5 seconds. What you would have to do is determine how much time has passed to get back to the 100% or the whole. All right? Knowing the half-life, that's why your note said if you know your half-life, you can determine absolute age. That was on the very bottom of your notes here. If you know the decaying rate or the half-life, you can find the absolute age. We know that the half-life is 5 seconds. We know that we are left with 1/8. So if we were able to count back to get back to the full, we know how much time has passed. How much time has passed? 5, 10, 15,
20.
20 seconds. So we know that this element is how old?
20 seconds.
20 seconds old, which means that the rock layer that it's in is how old? 20 seconds old. Do we understand?
Yes.
And that's how half-life works. So we're going to be doing some examples to explain that as well.
Okay, so can you put that back up? Okay, so when you did the first half, right? How come you shaded in that half, but then on the other half?
Because we were only left with this much. So we only take half of the half that's there. We only take half of the life. This is now gone. It only decays by half life. Life means stable. Life means what's there. Okay? Does that make sense? Okay. Ask your questions, because I told you it's a difficult concept.
That was 1/4. Then you cut that in half.
This was 1/2. Then I cut it in half, and now I end up with 1/4. Then I cut the fourth in half, and I should end up with 1/8. My bad. You're right. And this should have been 1/16. My math was off. So what we're left with is 1/16. Good pickup. We got it?
Yeah.
It was just a number error. Thank you. All right? Now we're going to do some examples, and by the time we get to the end of the examples, you will fully understand it, I guarantee. So what we're going to do is we're going to look at the song one more time, just the chorus and then that verse that deals with absolute. All right?
Oh, yeah. Features.
Here we go. Get absolute. The radiometric dating, unstable, isotopes decaying, nothing left to take the place you see through half-life. Used to measure its age,
A billion years for only half a decay. What's left is what we call stable. No decay. Show me absolute age.
All right, so again, get absolute. What are we talking about? Absolute dating. And how do we do it? Good. We know that unstable isotopes are just elements. Any elements that start to decay are called isotopes. So unstable elements are decaying, meaning that they are breaking down. They're not going to have nothing left of them, and there's going to be nothing there to take its place. And they break down through half-life. And that's used to measure what kind of age? Absolute age. This is just talking about an example how it breaks down 1 billion years. What's left is what we call stable. So that's how we use this, the stable amount, whatever's left, will show us its absolute age. And that's what we're going to be doing today. So remember that verse to the song. So what you're going to do is you're going to put your paper in front of you that looks like this. Okay? And your paper says, scientists locate the blank fossils in the geologic column, then use blank dating to find absolute age. What type of fossils?
Index.
Index, very good. Who remembers the clue as to how to determine what an index fossil is?
It's an index finger, and that's the point, and that's number 1. That's like the only one.
Exactly. Robinson says your index finger is also your finger that you hold up for number 1, is also your pointer finger, and index fossils are only found in one geologic layer. Or geologic, well, layer, yeah, we can't say column, it's the whole thing. Only found in one geologic layer, so we can point to it with our one finger, which is called our index finger, which is, they're called index fossils. All right, so scientists locate the index fossil in the geologic column, then use what, Jamil? Radiometric dating, very good. To find the absolute age. Got that?
Yes.
All right. Now below are 3 samples of geologic columns. The shapes represent our fossils. Our direction is we are going to label the what? What do you think we're going to label? The index fossil. Very good. We'll do the first one together, and you'll do the second two on your own. Look at the first one, analyze the first one, and then raise your hand when you found the index fossil. Brian. The hexagon, which is located here. Why, Brian?
Because it's by itself in that one layer.
It's by itself in that one layer. Now, let me ask you this. By itself is not the important part. The important part is that it's only in that layer. What if there were 6 hexagons here? Would it still be an index fossil? Yes.
Yes.
Because it's still only found in one geologic layer. The index fossil does not say there's only one fossil. It says it's found in one geologic layer. Because, remember, this represents past life. If we only found one fossil there, that means there's only one thing, one living thing. Let's say if this was a Etidophorus. I don't know, I just made the animal up. I mean, only one Etidophorus lived there. It's not possible. I mean, many of them lived there, but maybe they all descended in this era. So yes, doesn't mean one fossil, it means one layer. So here we have an index fossil. Look at the next two and label your index fossil. All right, Aaron. The star? Why? It's only found in that one layer. Very good. Question, Kwan? Okay, 1 second. All right, Kwan, index fossil in this geologic column?
The little circle thing.
Cinnamon rolls?
Yeah, cinnamon rolls.
So everyone has a good understanding of what index fossils are, correct?
Yes.
Okay, very good. So we've already identified our index fossils in those 3. So now let's take a look and just get a little bit of a better understanding of how elements decay, or how elements decay within the rock layer, and how we figure out the age of the element. So let's say that this rock, the lighter part of brown, represents the layer of the rock. We're not writing anything right now. The darker brown is your fossil. The Hershey chocolate bar is your element, okay? So we're going to say it's the element Hershey, or Hershey element. It has a half-life of 15 seconds. What is that telling me that it has a half-life of 15 seconds? Duran?
Every 15 seconds, half of that element, not element, fossil gonna go.
We're missing, when we say half of that, we mean half of
What's left?
half of what's left. Half of the stable portion is going to go away. So count 15. When you get to 15, say half-life. Go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Half of it has decayed.
Almost.
All right. Count another 15.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Half of what was there is gone.
I thought when you did half life, I thought it would cut this part right here.
No, it cut. Before we did that, we had 6 little squares. Half of 6 is 3.
Oh.
All right. Now 15 seconds.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
I went the wrong way. Sorry. Not doing it for me. I'm going to go from here. So the first 15 seconds was half-life. Second one was half-life. I don't know why my screen is acting crazy. If this is all of the element that we had left there, and we know the half-life is 15 seconds, and we need to get to 100%, and we know how much is 100%, how old is this rock layer?
30 seconds.
30 seconds. We start over. It's only 30 seconds. Got it? Okay. Now on your sheet, you have these words. Below are examples of rock layers containing a fossil. You will draw circles representing the element inside the fossil. Just put my screen up here. The rock layer is as old as the blank it contains. Patrick. Index fossil.
Oh, yeah.
Our direction is going to be to determine the age of the rock layer for each example. Now, this first time we do it, we're going to be breaking down, which means that we're going to start from the hole. We're going to go back in the past as it looked like a hole and work our way to the present, realizing what it has and how old it is, okay? So we're about to go back in the past, study the past, knowing what the hole is, and we're going to break that hole down, okay? The below rock layer contains what types of fossils?
Index.
See how I'm trying to drive this into your head?
Yeah.
Alright, so the below rock layer contains an index fossil with a half-life of 10 seconds. So we do know the half-life already. Alright, so we're going back in the past and we're going to use these pictures to determine our steps. So these are not 3 different layers or 3 different fossils. These are the same fossils, but they're progressing in different steps. This outside portion represents what?
The layer.
The time.
Layer. The fossil.
Below are examples of rock layers containing a fossil that you will draw circles representing the element inside the fossil. So what is this?
The element inside the fossil.
What is this? We have not. This is the fossil. Okay. Here we have our index fossil. We're going to draw the circles to represent our elements. How many circles are we drawing?
12.
12. Draw 12 circles. Like so. Those circles represent elements. Pieces of the element. Okay. After 10 seconds, count 10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half-life.
Half of what was there goes away. Half-life. So now we have how many?
6.
We're going to use it. We're using these different circles to label step by step what happens. So we started in the past and we're bringing it to the future, to the present. All right. After 10 seconds, what's going to happen? Half of what's there is going to decay. Ready? Count.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half-life.
And now we have 3 pieces of the element there. You need to make sure you drew that. How old is this rock layer? 20 seconds, because 20 seconds has passed. So, and the index fossil is 20 seconds because of the amount of element that's there. So it's 20 seconds. What percentage was the element in here? 100%. What percentage was in here?
50.
50%. Half of the 50% would have been 25%. Okay? Yes. Well, we just stopped because this just told us to stop and just asked us now that we're here how old. It didn't give you a specific time to stop. It just, at this point, now it's asking you how old is it.
Can it ever be 0?
Can it? Can it? You're always taking half of what you have there, so it can be point something 0.0000001, but you're always taking half of what you have. Nothing is half of 0. You can break it down more, but we can break it down more, But I just stopped here and asked you how old it was. It could go more, but this is just saying, if you were a paleontologist and you dug up a rock layer and you found a fossil and locating the element and you only had 25% and you know that the half-life is 10 seconds, you would have to go back till you get to 100 to determine how old it is. But we started from the past and brought it back to the present. Now we're going to start from the present and go back to the past as paleontologists do. Devin.
You found out that it's like 25% of the elements still left. Won't they have to have like a rock that has full?
They don't have to have a rock that's full, but they have to know the rate of decay of that element, so they can know how much of it to get to full. Mm-hmm.
How do you find out that happened?
Scientists study that. They study that to know. All right, good questions. So flip your paper over. And now we're here. Paleontologist. All right. So now we have this. You don't have this on your paper yet, but now we are going to build up, which means that we're going to start in the present and we have to go back into the past like paleontologists do. So, an element has a half-life of 5 seconds and its stable state is 10. How old is the rock layer? It's 10 of these little circles. How old is the rock layer? So what this is saying is a scientist dug up a rock layer. They found this fossil. They investigated. Jenna, look up here. And they saw this element was here. They know what this element is. They know that the element's half-life is 5 seconds. And they know that the stable amount of this element is 10 of these red circles. So then they have to now go back in time to determine how far can we go back, or how far do we have to go back in time to get this back to stable. Okay?
Yeah.
So let's make our first block look like this one. So we have 1 1/4 circle. Now we want to make sure that we label this as our what?
Element.
Index fossil. And this stuff inside is our what? Element. Our half-life is what?
5 seconds.
5 seconds. So how much time is going to pass before we build it back up?
5 seconds.
So we got 5 seconds to build up. So we're going backwards now. Count 5 seconds.
1, 2, 3, 4, 5.
Because building it back up a half. So build it back up a half. We're going to now have 1 1/4. So now it's going to give us 2 1/2. So you want to draw another circle here because we want to progress and show our time progressing. So after 5 seconds, we now have 2 1/2. Are we at its stable state?
No.
No. So do we have to go more?
Yeah.
How much time will have to pass? 5 seconds. After those 5 seconds, we're going to gain another half. So count 5.
1, 2, 3, 4, 5.
Full life.
It's not really full life. It's still half-life because we're gaining a half-life back. So now we went from 2 1/2 to 5. We added another 2 1/2. So now we have our index fossil that now contains 1, 2, 3, 4, 5. Are we at stable yet? 100%? No, we're not at 100% yet. So we have to let another time pass. How much time do we have to let pass?
5 seconds.
5 seconds. So, and going back in time, 5 seconds. Count.
1, 2, 3, 4, 5.
Half life. Stop saying full life because it's not really full. We're gaining another half of life, which means that we're going to gain 5 more, giving us a total of Are we at stable?
Yes.
So this is stable. So with that being said, how old is this rock layer? You want to write down this question. How old is this rock layer? How old is it?
15 seconds.
5, 10, 15. Only 15 seconds has passed for us to get from full to this. So this rock layer is 15 seconds. Here's another question. What percent of element is in this layer? We're only talking about this layer here. Bryson. So this went from 100 to 50. From 50, half of 50 would be 25. Half of 25 would be 12.5%. So it's 12.5% of the element is there. Yes. What would be 15%? 15 seconds. Time. Time is not in percents.
Oh,
I did, right here. That's 1/5. 15 seconds. It says, how old is the rock layer? 15 seconds. How old is the rock layer? Same thing, 15 seconds. I just wrote it right here. Same question. How old is this rock layer? How old is this rock layer? Same thing. I didn't write a number here.
Which one?
How much time has passed here? From here to here is 5 seconds. From here to here is 5 seconds. From here to here is 5 seconds. This question is asking how much time passed between these two. And between these two. And between these two. So we can count and see 15 seconds. All right? Now, what you're going to do is on the bottom of your paper, it's going to be your turn. Now you're going to play the role of a paleontologist. And it says directions, you're going to trace your object below. And the object is going to be your Twizzler. Don't open it yet. I'm going to explain to you how you're going to do it. But in a moment, you are going to open your Twizzler. You're going to place it in the box. And you're going to lightly trace it. Don't do it now. Just trace around. It doesn't have to be perfect. This is not really lead. It's graphite. The stuff that you call lead in your pencil. All right, no, we're not going to get sidetracked. And then after you trace it lightly, then you'll just go over and kind of trace it again with your pencil, not making it perfect. Now, before we do that, it says, trace your object in the box below. The box represents what? Index fossil. Don't say it after us, say it with us. The object represents what? Your element. We're going to let shading represent decay. So go ahead and open up your Twizzler and place it in your box. And trace it lightly. Yeah, trace it. I want you to trace it lightly and then take your Twizzler off and then make the line darker so you can see it. Bless you. No, you're not eating anything. We're not talking. You just trace your Twizzler. No, hold on to your trash. We'll throw it away at the end. All right, I'm ready to start. Okay, so now we have our element inside of our index fossil. Our element is going to have a half-life of 30 seconds. So, Duran, I don't need you to repeat everything I said. So in 30 seconds, how much of this element is going to go away? Half. So draw a line signifying half, and then hold your Twizzler in the middle for half. Because in 30 seconds, what's going to happen to half of this Twizzler? It's going to decay. So I want you to make it decay, meaning disappear, go away. After 30 seconds, you'll say half-life, and it'll go away. Here we go. 30 seconds. Not yet. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Half-life. So now we have half decay. How do we represent decay? How much time has passed? 30 seconds. So it took 30 seconds. What percent was this? 50%. Now, after another 30 seconds, half of what we have is going to decay. So right about here is going to be our half. So you want to represent your Twizzler at half. 30 seconds is going to pass. After 30 seconds, you need to make it decay.
Yes.
Here we go. Time's going. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Half-life. What do we do to represent decay? How many seconds?
30 seconds.
What percent would this be? 25%. In 30 seconds, half of the life that you have there is going to decay. So you want to signify what portion of it is half. It's right about here. It should be right about there. 30 seconds. Shh, quiet. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Half-life. I need some of you to mind your own business. What does, how do we represent half-life again? What percent is this? 12.5. How much time has passed?
30 seconds.
In half-life, we are going to decay half of what's left, which is going to be right about here. Don't bite your finger. I didn't ask any questions. Here we go. Decaying is quiet. It's not a noisy process. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Half-life. Shaded in. What percent was that? 6.25%. How many seconds?
30.
Now, if we were paleontologists, and this is all we found, what percent is this?
6.125.
6.25.
So they're half of each other.
Right. So we have 6.25 left. So, hold this in your hand. Do not do anything with it because it is still stable. Up here, I want you to write the element. Make this bigger. Right, the element has a half-life of what?
30 seconds.
30 seconds. At the bottom, I want you to write how old is the rock layer containing the, nope, be quiet, just write the above stable element. How old is the rock layer above containing the stable element? Patrick.
A minute and 20 seconds.
120 seconds, which equals 2 minutes. How much time has passed? 30. And a 30 is 60 seconds. That's a minute. 30 and 30 is another 60 seconds. That's 2 minutes. So your fossil left is 2 minutes old, which means your rock layer is 2 minutes old. Any questions? Yes. Make it disappear. This concludes this portion of the lesson.